All right, welcome to a video lecture on electric motors. What is an electric motor? To answer that, we should actually just start with the word motor. The Latin word is actually also just motor. It literally just means mover. And in English, we define motor a little bit more concretely, and we say that it is one who, or that which, imparts motion. That's it. That's all we say. Just anything in the world that causes some sort of motion, or rather imparts motion onto another thing. And so really, we can define motors as a lot of different things. You know, there's a classic example in the motor that's in your car that makes your wheels spin around and makes your car go forward. That is producing motion. We can also call the thruster of a rocket a motor because it's inducing upward motion in our rocket. We could even refer to our own legs as motors as we run or walk because they're inducing motion in the rest of our bodies. So really, talking about an electric motor is only really talking about one kind of motor that we're concerned with, and that is a rotational motor. And you can see a thing that I did not have time to draw on camera up here representing something that would spin, and like here on these wheels, for instance, in a Tesla car, you would have rotating motors, things that impart rotational motion. So imparts motion, rotational motor imparts rotational motion. So that's what an electric motor is going to end up being, is a rotational motor. And there are a ton of different kinds, but they end up really working down to the same principles. And before we get into that, why are these important? You know, what about electric motors would be relevant for the average person to know? Well, they're really prevalent in everyday items. I mean, if you have a fan on your desk, that's probably got an electric motor in it, probably plugs into the wall, that makes it spin around. Notice how it's rotational. We mentioned cars like Teslas. Those are very important nowadays. You've got your quadcopter drones that have become very popular with companies like DJI. Now we impart rotational motion to these rotors to make sort of 4 separate helicopters, and that pushes the drone upward. If you have a camera, or even your phone camera might have a tiny little motor in it, and if you see the lens of your camera spin, that's probably a motor doing that. And you know, if you grew up, not a lot of these around anymore, but if you grew up with a DVD player, the CD or DVD in there is going to spin on a little turntable. A more obvious representation of this would be a record player, but those are even further back in history. That, in the bottom there, is going to be a little electric motor. When we're talking about motors in engineering, these electric motors are so prevalent that really when you say the word motor, unless you're working in the particular context of like a gas-powered car or a rocket, you're really talking about these electric motors because they are so prevalent and so fundamental to really inducing motion in anything that moves on its own. So in getting to the real design, we've got to establish some fundamentals. It's easy to forget about them if you don't spend a lot of time with them. Therefore, we'll do a little review here. Now, we know magnetism at its base level as sort of these abstract bars that are usually red and blue, and they're marked with a north end and a south end. And we know that the north ends repel each other. The south ends also repel each other. And so these magnets would get pushed apart. But we also know that if we orient our magnets like this, then the south is going to be attracted to the north, and the north is going to be attracted to the south. Now, why this happens is a little complicated and involves a lot of sort of quantum mechanics. You know, you've got little photons going back and forth. It's very interesting, and I invite you to look into it, but it's kind of beyond the scope of this video. What we basically want to know is you've probably seen this, you've probably played around with it, you've probably had bar magnets on a table and thrown them around, and you might have even these things that we call magnetic fields. And we usually represent magnetic fields with these lines that I'm drawing here, and this is usually what they look like when we're talking about bar magnets. These are sort of lines and arrows that you can imagine going along here from end to end, and they indicate what force some other magnetic object in the magnetic field is going to experience. So we like to draw with these magnetic field lines, and really all that you need to know right now is that a bar magnet has magnetic field lines that look like this. And I'm also going to assume that you kind of know what electricity is. You know, let's cover a basic level here. So we have, let's say, a wire here. And we know that there's atoms in this wire and that those atoms have a bunch of electrons that I'm going to represent with these sort of E negatives here. And say we hook that up to a battery, and this battery has positive and negative leads. And if we bring that, say, to a light bulb, and back out to our negative lead, then these electrons are going to sort of move through this wire, and this light bulb is going to light up. These electrons moving through this circuit is going to produce some result that we care about and that's interesting to us, and we can do work with these electrons, like lighting a light bulb. And in our case, we're going to be using electricity and magnetism to generate rotational motion. Now, again, this is more complicated. In fact, what we think of as charge, because of Ben Franklin, actually kind of flows in the opposite direction. So just know that electrons moving is something we refer to as current. Current in a wire is really just electrons moving. And what you might not know is that these two things, electricity and magnetism, are actually the same thing. They're not even like the same thing or basically the same thing. They are the same thing, and we call it electromagnetism. It's convenient and intuitive to think of them as two separate things because we found these two applications of them that are different and utilize one aspect a lot more than the other. But these two things are effectively interchangeable, and this is going to end up sort of being the basis behind what we're able to do with an electric motor. And we don't have to know the intricacies of this combination, but just know that electricity, current passing through a wire, can be converted basically directly to magnetic effects like we have here. And you have actually probably utilized this before. Maybe in a high school physics class, you were asked to take an iron nail and then take a copper wire or some other metal, but some metal wire, and wrap it around that nail so that if we attach these two ends to a battery, so we can just do plus and minus here, what's going to happen is we're going to see electric current pass around in a circle around this iron nail. And by generating this circular current, these electrons effectively spinning down this coil of wire, we're going to generate a magnetic field. And that magnetic field is going to look exactly like a bar magnet. Exactly like a bar magnet. We're going to have a north end, we're going to have a south end. And what's fantastic about this is if we turn off these two positive and negatives, that magnetic field goes away. If we reverse it, we put positive over here and negative over here, what happens then is our poles switch. So we go north over here, oops, and we go south over here. So we have full control over this magnetic field, which is very, very helpful. And the strength of the magnetic field actually depends on how much current we're passing through the wire. And so this gives us a much more controllable thing than those just sort of permanent bar magnets that you might have played with in high school or when you were a kid. So again, just for visualization, say I get rid of these currents or these charges on the either ends of the wire, say with a battery or a generator of some kind, these magnetic field lines would disappear. This current would stop going through the nail. So what we have basically is we have this what can be kind of construed as a bar magnet. We'll call it an electromagnet, and has sort of a positive state where we have north and south. It has a negative state where we have south and north, and then it has a zero state where we don't have anything. So let's go back to our bar magnet. Say we had this bar magnet over here. I'm going to draw it sort of more 3D. And we attached it to something like an axle or a pole. Say we maybe attach a wheel to this pole, and we want this wheel to rotate. And we want this bar magnet to rotate, right? So we want to induce some rotation like this in this bar magnet. How might we do that? This is what's going to get us a motor, right? Rotating this bar magnet. So how might we do that? And ponder that for a second, because from what we've learned, you could figure it out, and the answer is really pretty cool. And the answer ends up being just take another bar magnet and put it near our bar magnet. Right here I have it at sort of a 90-degree angle. And what's going to happen is these norths are going to attract to each other, and if we have our bar magnet attached to an axle, that's going to cause the bar magnet to rotate. Now, our magnet has rotated and these forces are balanced. Well, what if we then take this magnet and we move it over here? Well, now what's going to happen here is this is going to rotate again. I'm going to erase that rotor. So we've rotated all the way around this way, and our north is now on this side. And you can sort of see where this is going. We're going to keep rotating this. It's going to go here. This is going to go here. Then we could put it here, and this will go here, and then we'll be turn all the way around, and we'll be back to our bar magnet here in the center, north. I'll draw the other north, and south, and our axle, and we have spun all the way around, and this has traveled all the way around. That's great. We have a motor, right? Well, you may have noticed that what we've done is we've traded trying to rotate one permanent magnet to trying to rotate another. So that doesn't really make sense, right? How are we going to rotate this? What are we going to do? Well, using our nail from before, with our wire wrapped around it, right? We can generate a north and south bar magnet on this. So what if instead of having this magnet going around here, we took 4 of these nails and we put the tops right here. And I'm going to draw this as an open circle. You'll see why in a second. We put them at the north, south, east, and west. And now we know that we can pass plus and minus through here, generate north and south, or we can pass plus minus like that and generate south and north. So we can put a north or a south on all of these tops of the nails. Remember, this is the top of the nail. The bar magnet is not going to be attracted or repelled by the bottom of the nail here. We're just dealing with one half of the magnet. Well, say we put north here, right? What if we just did that? We can turn off the rest and we can put north here. Well, that's going to rotate our north this way. And then, like before, it'll be balanced. We basically put that little permanent north-south magnet right here. And then, we turn this off. We turn this one off, and then we turn this one on. Well, now it's going to try to rotate this way. And then we turn this one off and turn this one on and turn this one on and in a circle. And that works great. Well, say we had more electric current than we knew what to do with. What we could also do is, say we're sort of halfway in between here. To get a little more force out of it, we could turn, this one's still north as we wanted, and we could put this one to south, and that's going to repel it. Right? And we could actually do that everywhere. We could put south here, and we could put north here. And that's going to, oh, you know what? I was drawing north to north being attractive. That's wrong. Oh man, okay, yeah. I'll just switch this. So north here, and we put south here. And now we have an attractive force going here. We have a repulsive force going here. We have an attractive force going here and a repulsive force going here. And that's going to spin our magnet in a circle. And as long as we can find a way to switch what poles these are going to, we can just keep rotating it. And you really could just like hook these magnets up. You're going to have 2 leads that are going to have the sort of positive and negative. And you could put them through like some kind of light switch or something like that. You could just fiddle these things in between each other, and you could manually sort of operate this electric motor. And this design was actually almost exactly invented by Walter Bailey in 1879. We now have more advanced sort of computers that we can use to control these things directly, and where you might see this kind of motor is in a type of motor known as a stepper motor. The reason we call this a stepper motor is because there are discrete steps, sort of 90-degree angles, where you can hold your rotor. So I can hold my rotor directly across, I can hold my motor directly on top, I can even hold my motor directly between. Imagine if I had put north here and south here. all of a sudden all these forces are actually going to go away because you have exact repulsion here and you have exact repulsion here. So we can actually get the states in between. We call this a stepper because we can go through all of these different steps. And in my mind, this is actually the simplest type of motor to think about. It was invented a lot later than the next motor we're going to talk about. I think this is a really basic thing to understand because we all did this with a nail when we were in high school, and the step from here to here is really pretty simple. You might have even taken a bar magnet on the table and just ran a bar magnet around it at one point and been like, hey, I can make this spin. Well, that's effectively what we're doing. A good analogy for it, perhaps, is say we have a donkey and say we have a carrot. Well, we're going to hold that carrot right in front of this donkey's head, and the donkey is going to want to eat that carrot. Say we attach a stick to his head and has a string holding the carrot in front of him. He's going to move for the carrot's going to move away from him. We want to keep moving the carrot just close enough that he stays motivated. We want to move the carrot away so that he doesn't eat it and we have to get a new one. The metaphor there being when this magnet is sort of locked in a particular state. So these are really useful in things like 3D printers. 3D printers, you need very sort of exact motion of the tool in the middle. And so that's probably the best application that I can think of for a stepper motor. They're not great for much else because it's very hard to control that whole switching mechanism, and because it travels in those discrete steps, it can be kind of jumpy. So it's not great for like long operation or steady, smooth operation, and it can't go very fast. Thank you, everyone who decided to watch this video. Acting like this isn't just an assignment. You know, like, if you enjoyed the video, like, and if you want to see the next one, subscribe. But really, all the resources I used for this video to learn about this stuff, I will include in the description of the video or the submission box. And yeah, I appreciate you listening.